Hello everyone. Today we are going to present the term paper on data encryption and decryption under the guidance of Professor Gautam Saha of IIT Kharagpur. The group members are Abhinav Kumar Jha, Anshul Rajendra Tembare, Payal Kumari Agarwal, Jagriti Agarwal, Kumar Tanmay, and myself, Tanuj Saraf. Now here's a quote by Steve Prentice who says, whether your data is in transit or at rest, it is vital to remember that neither state is secure. Data must be protected in both states, and encryption plays a major in this. Now, what is encryption and decryption? Encryption is a process in which plain text data is converted into something known as ciphertext, which is rather random and meaningless. It is a code that normal humans would not be able to interpret. And decryption is the reverse process in which we convert this ciphertext back to the plain text. The encryption is done at the transmitter end before transmitting the message, and then the encrypted message is transmitted to the receiver side. At the receiver side, this message is again decrypted back to get the message again. Now, encryption and decryption assure data security. Now, we generally use a key to encrypt the data, and then we use another key to decrypt the data. Next slide. Now, next slide. Next slide. Okay. So now depending on the key that we use, the two keys that we use, now whether they are the same or they are different, we can classify encryption into two parts, symmetric and asymmetric. Now in the previous slide, what we saw was a block diagram which showed how a password called United Kingdom has been encrypted. Can we move to the previous slide? Yeah. So we have the password United Kingdom, which is encrypted into a ciphertext, which is some random combination of alphanumeric letters, and then it is decrypted back at the receiver's end to get the same password again, United Kingdom. Now moving ahead, the table that we saw for the differences between asymmetric and symmetric encryption, we can see that the key that is used is same for symmetric and it is different for asymmetric. The two keys are known as public and private keys. Now, symmetric encryption is very fast as compared to asymmetric because of the fact that the keys used are less. Now, here we see a list of some popular algorithms for encryption, both for symmetric and asymmetric. Let us briefly touch upon the top from the list. For symmetric encryption, we have RC4, which is known as reversed cipher 4. Now, this is a stream cipher. It generates a pseudo-random stream of bits known as a key stream. As with any stream cipher, these can be used for encryption by combining it with plain text using bitwise exclusive OR. Decryption is performed in a similar manner. Now, this entire process is similar to the one-time pad, except that the pseudo-random bits that are generated rather than a prepared stream. To generate the key stream, the cipher makes use of a secret internal state, which consists of two parts, a permutation of all 256 possible bytes and two 8-bit index pointers. On the asymmetric side, we have the RSA algorithm, which is known as reverse Shamir-Adelman. It is used by modern computers to encrypt and decrypt messages. The algorithm is based on the fact that finding the factors of a large composite number is very difficult, and when the factors are prime numbers, this problem is called prime factorization. This method is also known as key pair generator. Next slide.
Moving on to underlying logic that is being used to generate this key implementation and encryption, we look at cellular automata. So what is cellular automata? A basic definition involves that it is a collection of colored cells on a grid of specified shape that evolves through a number of discrete time steps. In this case, we consider a grid of 8 cross n, uh, n cross 8, where n is an undefined number, that is the number of clocks, and 8 is the number of row columns that we have. Each cell of the grid having a finite number of states and a neighborhood definition. In cellular automata, there are various rules that determine how these cells interact and transition into next generation. So considering for 8-bit implementation, we would be having rules numbered from 0 to 256. The rules are then applied iteratively for as many time steps as desired. Looking into the next slide, we have rule 30. So this is the basic rule that is being used to generate this key, implement this key generation part. It is an elementary cellular automaton where each cell has two possible states, that is 0 and 1. And the neighborhood of the cells is its two immediate neighbors, one on the left and one on the right. Hence, we have three inputs here. We visualize rule 30 in a two-dimensional grid where each row represents one generation and the next generation of cells is computed and populated in the row below. Here we will implement this logic via, we will go to the next generation via clocks and to the new state. And the rule 30 is implemented as output for an 8-bit which is 000111110. And it is seen that it exhibits aperiodic and chaotic behavior, and hence it produces complex and seemingly random patterns from simple well-defined rules. Thus, we have a random seed at initial state, which is difficult to determine if we do not know about it. And then with any n number of clock pulses, we generate a random key, which would provide, according to rule 30, which would provide us the key for this encryption and decryption part. Now Tanmay will take over.
Rule 30 is an elementary one-dimensional cellular automation where each cell has two possible states, 0 shown in white and 1 shown in black. The neighborhood of a cell is its two immediate neighbors, one on its left and other on right. The next state of the cell depends on its current state and the state of its neighbors. The transition rules are as illustrated in this figure. The transition rules could be simplified as left, XOR, central, or right. Rule number 30 can be represented using the truth table shown here. Here N1, N2, N3 represent input cells and out is the output according to logic for three inputs. On simplification, using Karnaugh map, we get output as not N1 and not N2 or not N1 and N3 or N1 and not N2 and not N3. The shown pattern emerges from an initial state row 0 in a single cell with state 1 shown as black surrounded by cells with state 0 shown as white. The next generation as seen in row 1 is computed using the rule chart mentioned in the transition rule slide. The vertical axis represents time and any horizontal cross-section of the image represents the state of all the cells in the array at a specific point in the pattern's evolution. To generate random numbers from using rule 30, we use the center column and pick a batch of n random bits and form the required n-bit random number from it. The next random number is built using the next n bits from the column. If we always start from the first row, the sequence of the numbers we generate will always be predictable, which is not what we want. To make things pseudo-random, we take a random seed value and skip that number of bits and then pick batches of n bits and build the random numbers. Now, Jagrati will take over from the next slide.
Now, we will discuss the basic logic of the implementation that we are going to see. To perform the encryption, we require a key which we XOR with the given data input. The result is the encrypted data. To decrypt the data, we XOR the ciphertext, that is, the encrypted text, with the same key used in the process of encryption. The same key is used for encrypting and decrypting the data. For example, if A is the given data input, then A XOR key is the encrypted data. Then for decryption, we will XOR the encrypted data with the same key again, that is A XOR key, XOR key. So now key XOR key will become 0 and A XOR 0 will give us back the A again, that is the previous taken data input. The encryption algorithm is based on a cellular automaton in which we use its rule 30 as implementation logic to encrypt the input sequence into the random numbers. The given circuit and logic is implemented only using 74xx logic gates. For the key generation, here an 8-bit array is used. The initial state of the array will be stored in a parallel load, parallel out register. The next state of the register is also stored in a parallel load, parallel out register. The next state is derived from the initial state. The logic section that implements the rule is between the two registers. Since this is an iterative process, there will be a feedback from the next state register to the initial state register. At the start, before the feedback begins, the required key is given as the input into the initial state register. This describes the whole key generation circuit. For the encryption, we decided to go for the sort operation. Data is sorted with the sequence obtained from the key generation circuit. The key generation circuit produces a new sequence for every clock pulse. It is generated again and again. For the decryption process, we need the same setup that was used for the encryption. The key given to the key generation circuit must be the same key that was given during the encryption process. The key generation circuit produces a suitable key for every clock pulse. The ciphertext is given as the data input, that is, at the input of the XOR gates for the decryption. The sequence in which the ciphertext is given to the system is very important. The order must be the same as that obtained during the encryption procedure. Also, the clock has to be perfectly synchronized so that the data and the ciphertext are XORed with the same sequence. Now from here, Payal will take.
Here we will see how the circuit is implemented. Here is the list of components used in the circuit for implementation. We have used 2:1 mux for selecting between the key line and the feedback line. We have used 8-bit register for storing the previous state. As we know, for rule 30, we need to know the previous state of the row to generate the next state. We have used 8:1 mux, which is implementing the rule 30 of cellular automaton. We have used 2 input XOR gates for encrypting and decrypting the data. For displaying the data, we are using the common anode 7-segment display. Here, I will show you the implementation in the circuit maker software. Here, we have implemented the rule 30 and we are generating the key. First, I will show you the key used. We are using the key as 000111110. Here, the red line represents high state and the blue line represents the low state. Now, the select line of the 2:1 mux is currently at 0 state. Now, I'm running the circuit. Here we can see that the key is being loaded at the input of this register. Now, giving a unit pulse to this register, the data is being loaded at this register. For the Q7 bit, we can see the implementation of the rule 30. The left state of the left neighbor of this Q7 bit is Q6, which is currently at high state, and the right neighbor in a cyclic pattern will be Q0, which is at low state currently. So to this mux, the select line is 100, which is I4, which is results into high state, high output for this mux. Similarly, for Q6, which is currently is at high state, its left neighbor is at high state and its right neighbor is at low state, which results into 110, that is decimal number 6, and I6 gets selected at the output, which is at low state. Similarly, this rule 30 occurs for the other 6 bits as well. Finally, we see that here the key is being fed at the input of the next register. To load it into the register, we give a pulse to this register. After giving the clock cycle pulse, we can see that this key is being loaded at this register and is displayed here in the BCD 7-segment display as 31. Here, the key is of 8-bit, but due to limitations of this BCD display, it can display number from 0 to 9. So we have divided this 8-bit into 2 4-bit pattern. So the key generated is 0011 0001. That is decimal number 3 and decimal number 1. Now After the key is being generated, we will see how we are feeding the data and encrypting it into a ciphertext and decrypting it back. So the key fed here is 12, that is 00010010. After giving this key to the XOR input, we are giving another input as this key generated, and the XOR of this both this data is being taken, and this is the ciphertext, and this is again XORed with the same key generation as we are implementing symmetric encryption and decryption. After again taking the XOR of both the data, we can see that the output data is the same as the input data. That is, we are getting back the original data after decrypting it. This is how the encryption and decryption system is working. Now, we can generate another keys if we want. By selecting this select line as high in this mux, we can use this last previous key generated, that is 3 1 here, and this is getting loaded at this input of this register. Now giving another clock pulse to this register, this input gets loaded here, and again the rule 30 is implemented using this 8:1 mux, and here we can see that how the key has been changed. Here the key is being generated as some random pattern because the this display displays the number from 0 to 9, so it is out of the range of this BCD display. Here I will stop the implementation now, and moving back to the here we can see the observation. The key given to the initial state register was 00011110, that was decimal number 30. The content of the next state register generated was 31, that is 00110001. The data fed to the system was 12, that is 0010010. Ciphertext generated after taking the XOR with the key was 0010011. The same ciphertext was given as input to the decryption system, as we can see, and the output observed was 00010010. Now Abhinav will take over.
So talking about advantages, computer applications, software, and hardware all integrate encryption to accomplish objectives that users value. The first application is protecting stored files. The applications that protect a single file or a few files always use symmetric encryption to protect the file content. Full disk encryption. Many modern operating systems support full disk encryption, which protects both user data and system programs from disclosure. Device locking. Mobile devices and the data they contain are frequently protected by locking mechanisms that ensure that phone data is encrypted whenever the screen is locked, and that only the user can unlock the phone and its contents. Virtual private network. A virtual private network, VPN, is a way of creating an encrypted connection between a remote user and a site. By enabling remote users to seamlessly connect to the organization's network, VPNs provide a convenient way for organizations to operate across multiple locations. Secure web browsing. Each time a user visits an e-commerce website or a web-based email server such as Gmail or Hotmail, he or she does so through an encrypted connection. Secure messages. Secure messaging applications use end-to-end encryption protocols to prevent third parties as well as the service providers itself from having access to the plain text of messages. Encryption is generally used to protect the confidentiality of cloud data also. Now we come to the limitations part. Correctly implementing and properly managing encryption systems is a very difficult task. With the exception of specialized emerging techniques for computing with encrypted data for data to be used, it must be at some point be decrypted into plain text where it is vulnerable to theft. Users often store keys and then protect them with passwords, which are much more vulnerable because they must be something a human can remember and type. Now we come to the conclusion part. Symmetric encryption and decryption was implemented using 74XX logic gates. Random key generation was implemented on the basis of Rule 30 of cellular automaton. The randomness of generated key increases with every clock pulse. One major advantage of using Rule 30 to generate pseudo-random numbers is that we could generate multiple random numbers in a parallel by picking multiple columns into batches n bits each at random. A sample 8-bit random integer sequence generated using this method with seed 0 is 220, 197, 147, etc. For implementing Rule 30, we are using 8 multiplexer chips, that is 8:1, and 2:1 mux is used to switch between feedback and the initial key. With this, we come to the end of our presentation. Thank you.